Welcome back to the deep dive. Today we are tackling one of the really big paradoxes in modern AI. We have these large language models. They can debate philosophy, write pretty complex code, even pass the bar exam. I mean, masters of high-level reasoning.
Right. Symbolic stuff.
Exactly. And yet, ask that same, genius AI to multiply two simple four-digit numbers, like, say, 4,582 towns times 9,133
And
Africans.
it just completely falls apart.
It fumbles, it hallucinates, it fails spectacularly. It's kind of like finding out your rocket scientist can't make change.
Yeah.
And this lack of basic arithmetic reliability, it's actually a huge barrier, right, for using AI in critical things like finance or checking code.
Absolutely. So what's really going on under the hood?
Well, that's what we're diving into. There's a recent paper that seems to have cracked the code on this specific blind spot.
Yeah, and what's fascinating, I think, is that the problem isn't really about the model's raw intelligence, or the architecture's capacity. It's more about the quality of the training signal itself.
Hmm.
This research shows LLMs often fail because they struggle with a specific kind of memory problem. Basically, maintaining accurate information over long distances in the computation.
Long-range dependencies.
Exactly. So our mission today is to unpack this. We'll see exactly why standard training methods often fail for this kind of task, and, maybe more importantly, look at a pretty simple practical fix that seems to work by forcing the model to get its internal bookkeeping right.
Okay, but before we get too deep, let's just quickly address that old idea, that LLMs just predict the next token. You hear it all the time.
All the time.
But if that was literally the whole story, they couldn't possibly do complex reasoning, could they? Chain to thought and so on.
No, it's an incomplete picture. The transformer architecture itself can represent and execute algorithms. It absolutely can if it's trained the right way.
So multiplication is like a stress test.
Yeah, precisely. It's the ultimate stress test for figuring out if a trained model has learned a real computational algorithm, or if it's just learned some kind of flimsy statistical shortcut that falls apart under pressure.
Okay, that makes sense. So let's unpack this using the human analogy. Why is multi-digit math hard for an AI? You mentioned the scratchpad idea.
Right. Think about how you do it. If you multiply, say, $12 times 34.3.
Okay, yeah, I'd write it down.
You write it down. You calculate the partial products, the $2 times 4, the 1 times 43, the $2 is 33, the $1 times 33. You line them up, you add them, and crucially, you manage the carry number from one column to the next. That whole process is very explicit, step by step. It involved moving data, that carry digit, across columns. It's a long-distance data flow.
And the LLM has to replicate that whole thing where it's inside its hidden states.
Exactly. Inside its sort of ephemeral internal memory. That's the computational relay race we need to track. It has to pass the baton correctly.
Okay, so how does that connect to what the researchers found? You mentioned a core signal.
Yes, so the source material really pinpoints this. They identify the core mathematical signal the model must maintain accurately at every single step. They call it the running sum. We can maybe just call it C hat for simplicity, item hat K. This C hat is the single most crucial intermediate result it needs to keep track of.
And what is that conceptually?
Conceptually, it's actually pretty straightforward. At any step K in the multiplication, C hat is just the sum of all the new partial products that belong in that column, plus whatever carry number you got from the step before. And here's the key. If the model can successfully calculate and hold on to that running sum, that single C hat value,
Then it knows what to do next.
precisely, it automatically knows two things. The actual output digit for that column and the new carry number it needs to pass forward to the next column. That carry is the baton in the relay race. It links the steps together.
Okay, let's try that $12 times 3444 example again, just to see the C hat in action. We go from right to left, least significant digit first.
All right, so step one. K else, we just multiply the last digits.
Yeah.
$2 times 4 hill, that's 8. The running sum, C hat 0, is just 8. So the first result digit is 8, and the carry to the next step is 0. Simple enough.
Okay, easy start. Now $10 one. This is where it gets a bit more complex.
Exactly. First time we see complexity. The model has to sum the cross products, $1 times 4 plus 2 times $3, then $4 plus 6 is $10. Now the running sum, C hat 1, is this total 10 plus the carry from the previous step, which was 0. So C hat 1 is 10.
Okay, so the output digit for this column is the last digit of 10, which is 0, and the carry is the 1.
Exactly. The output digit C hat 1 is dollars, and crucially the new carry, $1, is nuller.
And this is where you're saying the standard models often mess up, getting that carry of 1 over to the next step.
That's the core of it. That carry, the $1 a one number, has to travel across the sequence, however the model represents it internally, and correctly influence the calculation for the next steps. Okay, W2, for $2, the only partial product is $1 is 3 to 3. The new running sum, C hat 2, is this 3 plus that critical incoming carry of 1.
Making C hat 2 equal to 4.
Right. And the output digit, 2 is 4. Carry is 0. So the final result is 408. This specific long-range relay race, passing a carry accurately, especially when you scale up to $4 times 42 digits or more, that's where standard models seem to consistently drop the baton, particularly in the middle digits.
Okay, so we've identified the failure point for forgetting or messing up the carry. Did the researchers actually, prove this was happening inside their models?
They did, absolutely. And this takes us to the core experimental proof in the paper. They set up a really clean comparison. They took two small, basically identical transformers, just 2 layers, 4 attention heads each. Really quite small.
Tiny by today's standards.
Tiny. And they trained both of them on the same task, multiplying pairs of 4-digit numbers. Model 1 was the standard approach, standard fine-tuning, or SFT, trained only on the input numbers and the final answer. The typical way we train these things.
Okay, input $, times B output $2.
Exactly. The second model used a technique they called implicit chain of thought, or ICT. You can kind of think of ICT as training with a vanishing scratchpad. They initially showed the model the full step-by-step work, like the intermediate calculations you do on paper. But then, during training, they gradually deleted those intermediate step tokens.
Ah, so they faded out the hints.
Right. They forced the model to internalize the step-by-step logic itself without relying on seeing the explicit scratchpad text to get the final answer.
Okay, so SFT versus ICT, what were the results? You mentioned a big difference.
Well, the performance contrast is just stark. It's really shocking. The SFT model, trained the normal way, basically flatlined, it languished below 1% accuracy on this $4 times 4 up 4 task. 1%.
Wow.
And it didn't really get better even when they tried making the SFT model a bit deeper. It consistently failed on those crucial middle digits like C33 through C60Rs, where the carry information has to travel the furthest.
And the ICT model, the one with the vanishing scratchpad.
100% accuracy.
Get out. 100% versus 1%. On the same tiny 2-layer model.
Yep. 100% accuracy. It learned the multiplication algorithm perfectly.
Okay, that pretty much demolishes the narrative that you just need, exponentially more parameters to solve these kinds of systematic tasks.
It really does. This isn't about scale, not at this level. It's a tight, controlled experiment showing a massive gap, pointing directly towards a missing mechanism in the standard training.
So how did they confirm why the ICoT model worked? Did they look inside?
They did, using some really neat deep diagnostic techniques. 2 main ones. First, something called logit attribution. Basically, they trace the influence of each input digit on each final output digit. The ICoT model showed exactly the right long-range influence patterns you'd expect for multiplication, input digit and a B dollars strongly influencing output digit TGI plus stress.
And the SFT model didn't show those patterns?
Not correctly. The SFT model just missed those crucial dependencies, especially for the middle digits. The connections weren't reliably formed.
Okay. And the second diagnostic, you mentioned probes earlier.
Right. And this is, I think, the most direct evidence for the whole bookkeeping idea. They used linear probes, specifically designed to find that running sum, that C hat number we talked about.
So they tried to read the model's mind, basically.
Kind of. They attached a very simple linear regressor, like the simplest possible probe to the model's hidden states at each step. And they asked it one simple question. Can you predict the correct scalar value of C hat, the running sum, just from looking at the hidden state at this position?
And?
For the ICT model, the probe could predict C hat almost perfectly. The information was right there, clear as day, encoded in the hidden states. For the SFT model, the probe failed miserably. It couldn't reliably predict the running sum at all.
Wow. So the crucial intermediate result, the C hat, was literally either present and decodable in the successful model or absent in the failing one.
Exactly. It wasn't a matter of degree or needing a fancier probe. The signal was either there, properly maintained by the model's internal workings, or it wasn't. It proves the failure wasn't about scale. It was about the lack of the right internal algorithmic organization.
Okay, so the ICT model won because it actually learned a structured algorithm, not just some fuzzy statistical pattern. How did its attention heads actually organize themselves to create this internal scratchpad? The paper mentioned something about an expression tree.
Yeah, the sources describe its attention structure really elegantly. It learned to organize its computations using a sparse directed acyclic graph, essentially. It formed a tiny, efficient calculation tree internally. The successful model figured out a perfect division of labor between its layers. Layer 1's attention heads basically acted like memory writers. They spent their time calculating all the necessary pairwise products, like A times BJ2, and storing those results in specific locations within the hidden state.
Caching the intermediate results.
Yes, exactly. Caching. Then, Layer 2's heads acted like a retrieval system. When it was time to calculate the output for a specific digit, say ET3, Layer 2 knew exactly which earlier positions in the sequence held the relevant cached products, where R tucket dairy plus JKR, and, crucially, it also knew where to retrieve the previous running sum, the carry, from the previous step.
So it's actual algorithmic execution. Look up A, look up B, combine them, store result, pass carry. Not just guessing the next token.
Precisely. It's learned computation.
And there was that detail about the geometry too, right? The pentagonal prism. That sounds wild.
It is pretty wild. It's like the model discovered an optimal coordinate system for doing math internally. The analysis showed the successful model arranged the representations of the input digits in its hidden states geometrically. They visualized it as this pentagonal prism built using a Fourier basis. Essentially, think of two stacked pentagons. One may be handling even position digits, the other odd. This specific geometric arrangement apparently makes the process of summing up those partial products incredibly efficient for the attention heads.
Wow. So the model is literally finding the best way to structure the data in its internal space to make the calculation easier. That's machine discovery, really.
It really is. It's optimizing its own internal representation for the task.
Okay, let's bring this back to practical application. Because look, the ICoT method sounds great, 100% accuracy is amazing, but using full chain of thought during inference, showing all the steps, that can add latency, right? It's not always practical.
That's a fair point. But the authors found something really encouraging. A small, practical fix that gives you almost the same benefit as ICoT, but without needing any of those intermediate CoT tokens at inference time. They call it auxiliary running sum loss.
Wait, hang on. An auxiliary loss. You're telling me that this task, where standard models fail 99% of the time, could be fixed just by adding one tiny extra loss function during training? That sounds almost too simple.
It does sound simple, but it gets right at the core problem. Is it just a hack? I don't think so. It seems to be fundamentally about guiding the model to learn the underlying algorithm.
How does it work?
Well, if the core problem is that the model isn't reliably tracking that internal signal, the running sum, CTAT, then the fix is to explicitly supervise that signal during training, make it visible to the learning process. So they added this tiny auxiliary loss. A small, simple linear head is attached to the attention output at each sequence position during training, and its only job is to predict the correct scalar value of the running sum, CTAT, for that position.
So no chain of thought tokens needed at all, just this little side task of predicting C-head.
Exactly. Just this minimalist guiding supervision signal. Tell the model, hey, whatever else you're doing, you also need to make sure this specific intermediate value is correctly represented right here.
And the result? Did it actually work?
It worked incredibly well. The accuracy immediately jumped from that dismal 1% for the SFT model to around 99% on the same 4x4 task.
99%, just from adding that small auxiliary loss.
Yeah. It's pretty much a textbook example of adding the right inductive bias to the training. You're not just throwing more parameters at the problem. You're giving the model a small nudge, a hint about the structure of the computation it needs to learn. You point it towards the necessary internal bookkeeping.
And it figures out how to do it reliably, how to stabilize that running sum internally.
Exactly. It learns the algorithm you actually need.
Okay, this is where it gets really interesting, I think, for anyone building or using LLMs day to day. Because arithmetic, yeah, it's kind of a toy problem in some way.
A very useful one.
Right. It's sharp edges. The fact that it's either exactly right or wrong makes it perfect for this kind of reverse engineering. And the lesson here seems like it should transfer directly to any task that requires multiple steps of reasoning, right?
Absolutely. Think about program synthesis, complex financial calculations, maybe long horizon planning or tool use, where the model needs to maintain some kind of state or keep track of conserved quantities over time.
Like balancing a checkbook or following a recipe or keeping track of variables in code it's writing.
All of those things. The core lessons seem to be pretty clear. First, getting the inductive bias right can pay off massively. Don't just scale up. Think about structuring the learning, maybe guiding those crucial intermediate steps.
Okay, structure over just brute scale.
Second, long-distance information flow, like passing that carry digit reliably, often needs some kind of explicit supervision or maybe a strong curriculum, like the ICoT approach provided. The model might not discover it reliably on its own from just input-output pairs.
So you need to help it build the internal connections.
And third, mechanisms that explicitly build, cache, and retrieve intermediate results, essentially, creating that internal scratchpad. Those are likely the ones that will win out for complex, chained reasoning tasks.
And if you're an engineer or a researcher and your own LLM is failing on some multi-step sequence task, you actually have a tool now based on this research, that C-hat probe. You called it the engineer's stethoscope.
Yeah, I like that analogy. You can implement something similar for your own tasks. If there's some key intermediate quantity that should be conserved or calculated correctly at each step, maybe it's a running total, a counter, the state of a variable, you can attach a simple linear probe to your model's hidden states during or after training. Try to predict that intermediate quantity.
And track the probe's error rate.
Exactly. It lets you see the computation or lack thereof instead of just staring at the final wrong answer and guessing why it failed. When that probe error drops close to zero, you have a strong indication that the model has actually learned to wire up that long-range computational path correctly.
That's really powerful. It gives engineers a way to diagnose the internal state, the internal algorithm, maybe for the first time in a really concrete way, tangible, measurable progress.
Right.
So we started out wondering, why can AI do philosophy but not simple multiplication? And it turns out the barrier isn't some deep philosophical limit on reasoning.
No, it's much more mundane in a way.
It's bookkeeping. Multiplication requires the stable relay of intermediate results that carry across many steps. And standard training, it seems, just doesn't provide a strong enough signal for the model to reliably learn how to stabilize that relay.
But with a bit of clever inductive bias, like that auxiliary loss.
The problem pretty much vanishes.
Yeah. It suggests the ultimate standard for LLMs, especially as we want to trust them with more complex tasks, shouldn't just be about reaching the right final answer sometimes. It maybe needs to be about showing they can reliably carry the torch from step to step, as the paper puts it.
So a final thought for listeners.
Well, if you're building models that need to handle sequences or reason about things where quantity should be conserved, think about money or dates or inventory or even symbolic states in logic, ask yourself this. Is the critical intermediate information, the invariant you need the model to maintain, is it actually being made visible during training? Can you maybe bake in an auxiliary signal like that running sum loss to help the internal algorithm learn to maintain the integrity of that sequence? Because if you can, your model might just stop failing on those crucial middle steps. That's where this mathematics of large language models really starts to prove its practical worth.